Welcome to the SOFiSTiK online documentation. In this video, we show how to do a dynamic analysis of a drained passage with moving loads. To introduce the basic workflow, we calculate a single passage, so one drain type and one speed. The calculation is done in our new analysis framework SOFiSTiK. The command structure of the module is organized in individual tasks. We use the task MLT for moving load drain analysis. In the task, we define the analysis settings. First, we define the damping properties of the structure for the dynamic calculation. The codes usually provide damping values in form of a damping ratio given as percentage of the critical damping. Here, for example, an excerpt from UIC code 7762. These damping values are usually intended to be valid over the complete frequency range of interest. In our analysis, we do a numerical time integration. Here we will use Rayleigh damping, which models the damping matrix of the system as a linear combination of mass and stiffness matrix, with the factors A and B for mass and stiffness proportional damping. In this approach, it is not possible to provide a constant damping over the frequency range. Instead, the damping is frequency dependent. So different modes of the structure will have different damping ratios. However, we can specify two frequencies for which the given damping ratio will be exactly fulfilled. In the example on the right, we can see the damping ratios for two sets of factors A and B plotted over the frequency, here depicted in the form of the angular frequency. A and B can be calculated such that the desired damping ratio is matched at two given frequencies. In this example, the first set of factors has been calculated to match the desired frequency ratio of 5% at the angular frequency of 1 and 10 Rad per second. The second set has been calculated to match the desired damping ratio at frequencies of 1 and 20 Rad per second. In the range between these frequencies, the damping will be slightly below the desired damping ratio, so on the safe side. In SOFiSTiK, you do not have to calculate the factors A and B explicitly. Instead, you can specify the desired damping ratio and the two frequencies where it should be fulfilled exactly in the group command. We recommend to set these two frequencies as the upper and lower limit of the frequency range of interest. Here we set the first frequency as first eigenfrequency of the structure and frequency 2 as the eigenfrequency of the third bending mode. Note that we use a minus for the group number to define that the settings apply to all groups, and that the group command can also be used to vary stiffness and mass of the structure. In the next step, we specify the analysis load case number. Generally, it is possible here to specify a load case number containing loads. These loads will be applied as stationary loading from the first time step on. However, for the current workflow, this option is not relevant. So we set here a load case number that has not been used before and contains no loading. Next, we define the settings for the time stepping. First, we choose the method for the numerical time integration. We recommend the generalized alpha method, which provides the possibility to use additional numerical damping to get rid of spurious high-frequent response. The amount of numerical damping is set with the parameter rho infinity. In this example, we set it to 0.8. To set the total time of the analysis, we use the auto option. With this input, the total time of the analysis is set according to bridge length, train length, and train speed to fit the time that the train needs to pass entirely over the bridge. Next, we define the time step size with item dt. We can either explicitly define the step size or use a convergence study to find and verify a suitable value for it. In this example, we show the second option. The convergence study for the time step choice can be requested with the DTC command. Here, we start with an estimation for a reasonable time step size. A recommendation that can be found in many sources is to choose the time step not bigger than 1/20th of the period belonging to the maximum relevant frequency. We also follow this approach and set it by providing the maximum relevant frequency in the DTC command with fmax. We recommend to set the eigenfrequency related to the third bending eigenmode here. With the resulting time step size, a dynamic analysis is then carried out, and for a specified result type, here nodal acceleration in gravity direction, the result time curve is computed. To check if this time step size already provides a good resolution of the problem, then the result time curve is next recomputed using a smaller step size. Verification is considered successful if the result does not change by more than a certain tolerance. If the verification is not successful, the time step size is further reduced and checked again for convergence. To understand how the convergence study works, we will take a look at the report of the convergence study to explain how it works. For each run of the analysis, you can see the applied time step size and the resulting number of steps. As it is difficult to qualitatively compare two time histories consisting of many time steps and result values, we monitor three representative values: maximum, minimum, and the root mean square of the result time curve. Here, the start value for the step size already was a good choice and yields almost the same results as for the reference time step. We can also check this in the plots that depict the result time curve for the chosen step size and the one for the reduced step size, which is the reference. The step size that we determined and verified here as sufficiently accurate can then be requested for the actual analysis by setting dt auto in the step command. After selecting the time step, we also decide where and to which amount the results of individual steps should be stored. This is also done in the step command with lcr_count. With this setting, we specify that the analysis load case given at LC should be taken as base load case to save the first time step. With int, we specify the storage interval for the results. With int 10, for example, the results are stored at every 10th step. If you have a small time step for accuracy reasons of the numerical time stepping, we nevertheless might not need the results at every step and could select a coarser storage interval with this setting. As the storing of the results takes some time, this is a reasonable way to speed up the analysis. We will also come back to this point in the next section. After setting the details about the numerical time integration, we select with the move_L command the load train, which we request by the load case number where we have stored it in the load train definition. Furthermore, we define the speed and the track where the train passes over the bridge. For the track definition, we use the axis from the CABD-based model. The axle loads of the load train are usually given as point loads. However, many codes allow a distribution of the train axle loads to take into account the load distribution by rail and sleepers. For this purpose, we provide the options LDA and LDB, which enable a further distribution of the axle loads in single loads or line loads. These two items can also be combined, an option that we show in this tutorial. With these settings, we have calculated the passage of a load train over the bridge. If we have stored the results of individual time steps with the settings LCR and int, you can now display them with graphic and use the available options, for example, to get an impression of the train passing over the bridge and also about the load distribution. As final point, I want to show you how you can store results of the analysis for further post-processing and checking. Here we have two options. First, the hist command. With this you can store the time history for a selected result type at the selected point of interest. Here, for example, the bending moment My at the start of beam 10,012, which is located in midspan, is stored under the storage number 9000. You can then plot the time history with the result viewer. We will show this in the post-processing section. The second option is the EXTR command. For a selected result type, here for example bending moment My of beam elements, the maximum and minimum results of the passage at every position in the system can be stored in the given load case number. This gives the envelope of the requested result for the complete train passage. After the explanation how to calculate a single train passage, we will show in the next video how to efficiently set up the analysis not only for one passage but for many.